Okay, let's look at the homework 3.3, 3.4, problem number 8. All right, so we have a rectangular solid with a fixed surface area, 181.5 square centimeters. And we want to find the dimensions of the largest box we can create. All right, so let's do that. Right, so you have a rectangular solid, so it's going to look probably like something like this. Right, then let's see, you can't see that side, you cannot see that side, you cannot see that side. Then you have x by x is the base, then height is say y. Right, so the surface area, say A, can be expressed as, right? So the base, the bottom has a x times x, so x squared, and the top is going to be also x squared, so you have two of them. So you have 2x squared, right? Then the side wall is x by y, so you have x times y. Alright, and there are four of them. You can see that there is one in front, and one on the right, and one in the back, and one in the left. So there are four side walls, so you have multiplied by 4, right? So this is fixed at 181.5. Alright, so we have that. Then the volume, so we want to maximize, the volume V, which is equal to, right, volume is simply x times y, right? So since we do not want to deal with two variables, I'm trying to get rid of one of the variables, so I'm going to try to get rid of y using the first equation. Alright, so first I'm going to subtract 2x squared from both sides, so we have 4y, 4xy, I meant 4xy is equal to 181.5 minus 2x squared, right? Then, to isolate y, I need to get rid of 4x. So I'm going to divide through by 4x, right? So y is equal to, right? So 181.5 minus 2x squared over 4x. Alright, so that's y. So let's plug that in. Alright, so the volume can be written as x squared times 181.5 minus 2x squared all over 4x. Alright, so you can cancel one of the x and x here, right? Then we can just distribute x, we get, right? So we're going to distribute x to the first term, which is 181.5 over 4 x, right? Then distribute x to the second term, you get the negative, right? 2 over 4, I'm going to write it as 1/2. Then you have x cubed. Alright, so we need to maximize that on an interval, right? So x has to be at least positive since it's a length, right? but x cannot be too big because let's say you use entire surface area just for the top and the bottom. So that would be the biggest x we can have. So that means that let's see, so the entire surface area is 181.5. So the half of that would be 181.5 over 2, right? Then that'll be just one of the either a top of the bottom, so x squared has to be um, less than that number, right? So take the square root. We can see that it's a square root of 181.5 over 2, right? Right, and I don't need that, so I'm gonna just erase that. All right, let's take a derivative. So let's see, v prime of x is equal to, right, derivative of this is simply 181.5 over 4, right, minus 3 over 2 x squared, right? Let's find a critical number by setting that equal to 0. So setting that equal to 0, we can see that first we can add 3 over 2 x squared to both sides. So you get 181.5 over 4 is equal to 3 over 2 x squared, right? Then we can just multiply both sides by 2/3, right? So that will get you 181.5 over, right? So 2 and 4 cancel out. You have 2 on the bottom, so 2 times 3 is 6, right? Is equal to x squared, right? Then by taking the square root, we find x equals plus or minus square root of 181.5 over 6, right? So those are the critical numbers, and we don't have to look at the negative one since the interval is from 0 to square root of 181.5 over 2, right? So we just look at the positive one, right? Let's make sure that we'll actually get the maximums there. Just looking at number line, right? So starting from 0 and ending at the square root of 181.5 over 2, right? Don't worry if it looks kind of bad, but here the critical number is square root of 181.5 over 6. All right. So before that number, so it's a really small number, you can see that this is going to be a positive quantity. So it's going to be positive here. And if you pass that point, then it's going to, this guy is going to be larger, so it's going to be a negative quantity, right? So we can see that, you know, the volume function is increasing here, and after the critical number decreasing here, right? This will indicate that you will have a maximum here, right? So let's find that value. Let's see. So I'm going to use a calculator, right? What's oops, right? What's one square root of 181.5 over 6? Oh, it's actually 5.5, right? So this is equal to 5.5. Okay, then y value is going to be y is equal to, so we have an equation here, so we just have to plug in 5.5, so 181 5.5 minus 2 times 5.5 squared divided by 4 times 5.5, right? So let's do that. So it's let's see, first 181.5, right, minus 2 times 5.5 squared, right? Get that. And then you divide it by 4 and also divide by 5.5. Alright, as it turns out, y is also 5.5. Right? So volume is going to be, right? So it's all 5.5 for 5.5 squared times 5.5, so it's a 5.5 cubed. So that's going to be, so 5.5 raised to the third power is 166.375. Alright, so let's plug it in. Alright, x is 5.5 and y is also 5.5. Alright, then the largest volume is 166 times 375. Alright, so let's check the answer. Okay, I came back and looks like we got all these correctly. Alright, that's it. I hope that this was clear.